Good morning, everyone. Let's finish the last part of this chapter. So last video we talked about the backtracking search algorithm. So this is the basically is just like an improved DFS or DFS with constraints. Okay, and then we talk about we want to improve the efficiency. So the idea or the philosophy is just like we want to determine unsuccessful solution earlier, so detect a failure earlier, and then we can stop the further search, so that will save our time, and then we can perform or we can find the solution earlier. And then we talk about the most constrained variable. That means some variable which have more constraints to others. Okay. This one is different. Most constrained variable means for this variable has a least number of remaining legal values to choose. So we also call them MRV. So it's the same as the most constrained variable, MCV. For example, we talk about we want to choose those variable first because they have less number of values to choose. Okay, we can find the solution earlier. And then we have the most constraining variable, means this is similar. Just like either we have more ties with others, and then we start with those variables first. So that means we perform or we add more constraints to others. So that means there's less choices for others to choose, and then you can approach to the solution quickly. So that's why we choose this one first. Okay. And then we also have another one called the least constraining variable. So this is a little bit different. That means the most constrained variable is like itself. That means the less number of legal values to choose. And the least constraining value means if we choose this value, because the previous one is talking about a variable. So if we choose the variable, which value to choose, so we use the least constraining value. So maybe you only have, for example, we found the variable which can pose more constraints on others, like the SA or SA. And after that, SA also maybe have several values. Which one to choose? To choose blue or to choose R or to choose green? So this one will look at least constraining value. That means which value to choose. Okay. First one, you find a variable, and then which value to choose. So this one will be decided based on the impact on other variables. If we choose a value for this most constrained variable, and then it will provide more choices for other variables. So that means it's easier to find a successful path, successful assignment, complete and also consistent. If we choose another one, which may make the case, which may have the case there's no legal value for other variable to choose, so that's not good, okay? So it will maybe terminate that search, and then that search is waste. If we can start with a least constraining value, then with the possibility to find the solution will be better, okay? Will be highest. So this is the idea. So that's the two important things we want to use in improving the backtracking algorithm. Okay, so we'll use most constrained variable and the least constraining value. So first one, find the variable, and then next identify the value. Okay, and the first one is most, the second one is least. Okay, so easy to understand, remember. So we already mentioned about this slide as well. Okay, so that means whether we assign a red or a blue. If we assign a red, we still allow 1 and 1 for these two states. But if we assign a blue, there's no legal value for this state. So this is the reason. If we choose blue, it will just waste. So that means before we do the assignment, we'll check whether this will pose significant challenges for other assignments, because you haven't finished the assignment card. It's not complete. So this is the reason. So that means which value to choose. We choose this least constraining value. Okay, least constraining value. This calculation should be very easy, because you only have a limited number of choices, and then have a limited number of constraints surrounding or pertain to this one. So it's not like this one will be pertain to all of other elements or other states. It's only the labeling cut. So related to this state, there's only a view constraints, and then you just only to check those constraints. If I choose this value, what will be the problem? How many choices for the constraint state, or the tied constraint, tied state, tied states. For this one 1, this one 1, this one 0. Of course, we will choose the least constraining value here. Rather than using blue, we use red, because this is more promising to find a complete assignment. Okay, this is the reason or the motivation, the idea why we have this design. Right? So that means when we understand something, it's better to just understand the what is going on behind, rather than just remembering. Right? If I confuse whether I need to use least or most for variable and value, but we still can develop the solution by ourselves, then you don't need to remember. You can just use an example. Okay? To at least you know we need to find out the extreme case, most or least. Whether use most for variable selection or least for variable selection, you can just, based on your understanding, to deduct the result. Okay, now we want to continue with the last instruction video. We want to talk about how can we improve the DFF algorithm. So that means we said that is DF is not complete DFS. Then we give a new name called backtracking, because each layer we only handle one variable, and then we can arrange the variables in a pre-ordered way. Okay, but you don't have two. Okay? But just like each layer, you will only handle one. Which one will be handled? It depends on the search. But you only you choose one variable. That one will be the next layer. And then which value to choose, and then you use least constraining values. And which variable to choose, use the most constrained variable. Okay, this is the idea how we can improve. So we said for this is the same algorithm as before, just the backtracking algorithm, no change. Okay? So assignment, select one variable, and then select one value. If you can finish the sub problem, you return the result. Otherwise, you cannot. You need to go with all the possible values. If you exhaust all the values for this variable, you still cannot find the assignment, means there's no solution for this sub problem. Then you can only reach this clause. You return failure, means no complete assignment for this problem. Okay. And then to improve the efficiency, we want to apply, that means the prefers two hints. One is the most constrained variable, the other one least constraining value. Okay, so we apply inference based on the two previous hints to reduce the space of possible assignments and detect failure early. So if there's a failure in front, do you need to go further to reach the end? No need, correct? So that means when we are on the maybe a cross, we have seen a dead end in front. Don't you need to just drive your car to reach the dead end and then go back? Yeah, if you cannot turn, you may have to do that. You reach the dead end and then turn. But if you can turn, it's like maybe 4-stop cross, you can turn left, turn right, do not go directly. Okay? This is the same strategy. We want to avoid unmeaningful search. We want to perform as much as possible, as much as possible, meaningful search. So this is the idea. And how to implement this? Just use the previous two strategies. Find the most constrained variable and find that is for which one? For this one, correct? And then if you find the most constrained variable, which value to go with? So you don't need to just use order domain, for example, already ordered. And then you will just choose the least constraining value to choose, rather than just use a pre-existing order for the values. You will choose one which is least constraining value. Okay, so this is the idea. So let's look at this one. We said it's called early detection of failure. Okay, so we apply inference to reduce the space, the same. So the example like this one. So this is the example. For example, in the previous example, we already know we can apply this color rather than use another color, because why we choose blue, we choose green rather than another color. The reason is that we can detect failure earlier if we apply some different color. For example, you can try maybe red or green, blue. Maybe you can find that there's at least one. Okay? Later we show the result. At least one, we have a failure. We can detect before we assign the color. That's why we choose this one rather than choose that one. Okay? Let's look at how to detect the failure earlier. So the first strategy is called forward checking. So like the previous one, we said we can detect the failure earlier just because we do the checking, the forward checking. So that means if we assign this value, and then what will be the problem it will cause. If there's an issue, we have a failure in front, we'll stop assigning that value. Okay, so like keep track of remaining legal values for unassigned variables. So that means for each value we will track. Okay, track, and that means for this value we will detect failures. We will detect whether it has some issues for others. Okay, for the unassigned variables, each value of the unassigned variables we will track whether has some problem. And then if we find a problem, for during the tracking we find a problem, we terminate the search. That means we are not assign the value because this one will have a failure in front. So terminate the search when any variable has no legal values. So you keep tracking. Maybe during the tracking you will result an empty value set for a variable. So you may not just like because of directly check these variables. It's just because you are checking another one. If you assign a value for another variable, but it will have a tie to this one. And then because you choose one value, so maybe you cannot choose some values for another variable. And then if you, based on a lot of constraints, you just delete all the possible values for this variable, and then you result an empty domain, empty legal value set for another variable. Because for all the unsigned variables, we maintain that states whether you will have a variable without legal values. Okay, if we found this situation, that is a warning. That means we have to backtrack. That's called backtracking back to the previous state and tracking the states of each unsigned variables. Okay, this is why we call it backtracking with some forward checking, and then next one we have another strategy. Okay, so in a word, just like when we perform the search, we track the hashy state, the state of each variables. If there is a variable which is non-hashy, means this search will be a failure, and then we have to back to the previous step, choose another value for the current variable. If there's no remaining values for this current variable, we have to backtrack again. So just one step. Okay? So if you find a danger in front, okay, we don't continue with this one, danger, and then we go back. Whether there's another one, we can do like this way. So if we can go, we go further. If we cannot go, we stop. We back up a step to the previous state. Okay. For example, let's look at this one. Just using an example. So initially, this one is this arrangement for each variable. We can choose all the 3 possible values RGB. Okay, RGB. And then, for example, we assign the WA first to be a red, and then we said that we need to track all the unsigned variables states. Okay, that means whether we delete some legal values or make some previous legal values to be illegal. So that means because there's a constraint, right? For example, this WA is tied with NT and SA. If WA is red, NT cannot be red, SA cannot be red. So you have to delete the red value from the NT domain, SA domain, right? Okay, or the legal value set domain, we can say maybe unit is fixed, and then using a more accurate language should be delete a value from its legal value set because they are not legal anymore. So NT is here, SA is here, so we delete red. This is the idea. Red cannot continue, and then we get a new states for all the unsigned or signed. Okay, you can still put that one. So that means new states for the variables. Okay, like this one. So there's no red values for NT and SA now. And then continue for the next one. And then we can choose either NT or SA, right? Either NT or SA. You can find that they have two legal values. So that means most constrained variable. You can see it's like this one. This is 2. Most constraint means has less legal values. This is 2, others are 3. 3. So you can choose either one. Okay? So maybe we ordered like that way. So we may choose the NT first. Oh, maybe. Okay, this is something wrong. I think it's yeah. So this one we applied another strategy called most constraint variable. So that means which variable to choose. In fact, Q. So you can find Q is tied with this 1, 2, 3. 1, 2, 3. And the NT, in fact, is also tied with the 3. Of course, this one choose Q is just like a choice. You can choose the NT. Does not matter because NT and the Q, each of them has the same. Maybe you also want to try SA. SA has the most constraint. So that means, for example, for this one, if you choose this one, choose this Q. Okay, choose this Q. For example, this is just like for example case. In your search, if you meet this case, you have chosen Q, and then which value to choose, you will look at the use forward checking. Why we use forward checking? Because if we choose some other values, maybe it will make some variables legal value set be empty. Okay, so that's why we choose this color instead of other one. Let's look at, for example, if you choose Q, you choose red. Okay, what will happen? You choose red because Q and T are tied to each other. Q and NT are tied. So you choose red. Red is not in this NT, so there's no problem. And then NSW and SA. NSW cannot choose this one, and SA is not in that one. So choose red seems no problem. Okay, that's great. So red is not an issue. But if you choose the blue, let's look at it. If you choose blue, and then what will happen? So, but you can find if you choose red, you delete. Let me see. This one and NSW choose. That means you reduce one. So you post one constraint like you reduce one. If you choose red, choose red like 1, and then if you choose blue, so Q is blue. Q is blue. And Q and NT, you can find Q and NT are labeling, so this one cannot choose blue anymore, and the SA also cannot choose blue, and then NSW also cannot choose blue. So you will reduce by 3. So that means you will assign, you will pose 3 constraints. But if you choose green, seems let's look at how green is 1. So green. So this one choose green. And the NT also cannot choose green, and then SA cannot choose green, and NSW cannot choose green. So this one is also 3, So you can find why we don't choose red. We choose either blue or green. Just because of this one, we have the most constrained. This is the most constrained variable. Because this one we reduced 3 legal values from other 3 variables. So that means you will possess more constraints and then reduce your search space. For example, like if you choose the green one, you only have 1 choice for NT, and also 1 choice for SA. So you can quickly decide 3 variables next. So for Q and NT and SA. If you choose red, you will still have 2 choices for here for NT, and this is red, we reduce 1. So this one is also have 2 choices. So only the constraint for this one. And then for the SA, still have the same, so there's no problem for this one. You have to have 2 by 2 by 2, cut 2 by 2. So combination. But for this one, you reduce it by 1, and then reduce this one by 1, you got 2. Reduce this one by 1, you got 1. Cut. You have 1 by 2 by 1. Because you reduce this by 1, and reduce this by 1, reduce this by 1. But for this red, you only reduce 1, but for green, you reduce all of them by 1. Okay? So this is 8, this is 2. So the number of combinations have been dropped. So you can find here, we will choose a most constrained variable. So of course this one we choose the Q, but in fact maybe NT is also fine. You can also confirm this is the most constraint. That means we want to look at how many constraints it will pose to other variables, and then we choose the one with the most number of constraints. Okay, if we choose a value for that one. Okay, this is the idea. Okay, if we assign the value for this one, and then because this is green, we already do this analysis. This already choose green, and then the labeling cannot choose green anymore. So that means that we need to delete labeling 1 NT and SA green and NSW green. Okay? So you have two colors, one color here. Okay. So now the search is easier, correct? And then NT is only one choice, and SA is one choice. So search the rest is easier. After you got these things, you almost get the final result, correct? So only V and the T, correct? So next step, we choose the V, okay? We choose V. You can find here, from here to here, why we don't choose NT and SA, we choose V first, because you know V is labeling with NSW, and NSW, if we choose a blue color, it will have a for labeling V and SA. So this one there's no problem. We choose blue, this one still can choose red. But if we choose blue, this one cannot choose anything. So this one will reduce the constraint by 1. You suppose have one more constraint. Okay. And then, for example, if we for example, we choose NT, let's look at how many constraints it will have. For example, choose this one, and this one is labeling with Q and ST. WA already assigned, Q is already assigned, so no need to consider. Only one is SA. You choose this one is NT is blue, and SA is labeling. This one will make it to empty. SA also empty. So that means that this assignment is also will pose one constraint. So start with this one. Similarly, you can perform this one maybe as well. And the SA is the same. SA and NT are the same. If you choose this one in blue and label instead NT cannot be blue. So and SA is also related to NSW. So NSW also can. This one is 2. We have 2 constraints for this one. So while we choose V is posed how many constraints. V is related to SA and NSW. So V is choose blue, and then NSW cannot be blue, and SA cannot be blue. So this one is also 2. So that means, but for most constrained variables, we have 2 choices, whether V or SA. So V and SA. This is SA. Same. We mentioned SA first, and then V. but the NT is only 1. So that means during the forward checking, we always use the most constrained variables, and then if we have multiple choices, you can choose either one. Okay, you can choose either one. So here, for example, we choose this V first. Okay, we assign the blue because this one will reduce the most number of legal values from the existing types. Okay, existing types. And then if this one is blue, is already assigned, and then we delete this one to be empty. Okay, we mentioned V is constrained with SA. And then if this one is blue, they are not be equal. V cannot be equal to SA, so delete this one. And similarly, so V is not equal to NSW. So this one is blue. This one cannot be blue. There's only one value left. Okay, this is a new one. And then during the tracking, you find a one with a empty legal value set. So you don't need to perform the search now. That means it's not possible for this one to find a solution. Okay. So we have backtrack. How to backtrack? So that means this one is not possible. The reason is just because we assigned the blue value here. Okay? Blue value here. So that means you have backtrack to here. So cannot use blue, so you try another one. Okay? Try another one. So that means now you need to calculate the most constrained variable again. Okay? So now you delete this one. You have a new state, which is this one. Okay, just backtrack. So this just get rid of the blue from that legal value set for the V, because this search is not successful. Okay? You try the third one first. This one cannot be possible, so this one is deleted. Because it's deleted, there's no more constraint to others, so you don't need to update other variables legal value set. And then you just get a new state without this value, and then you also have the only change is this constraint. Okay? Well, what's the constraint number for this one, and the others no change. And then you find the most constrained variables again, and then do the search. Okay, so this is the basic idea for this one. And then in the search, in fact, I want to clarify in the search, because we are already, you can find that we are loop over all the possible values. Okay? So only if we have no possible, for example, we still have 2, so we don't go back to another variable. We just go with the remaining variables first, because we know we have a for loop. Okay? We have a for loop there. We have for each value in the order domain values. Of course, here we are not use order domain. We use the most constrained and least constraining value. So that means we will try other values first. Okay, we'll try other value first. So that means we still can try the rest of values. We backtrack to here. This one does not good. Okay, that's not good. And then we go with the previous red and green. Okay, red and green. So we already know red is opposed 1 and green opposed 2. So we'll try green next. Okay, try green for the V. We'll assign green. Okay. And then we didn't show that one, but anyway, we just we do like that way. And then let's continue. So forward checking is a first strategy. In fact, we have another called a constraint propagation. So that's a second strategy. So what is called a constraint propagation? So that means initially we already know, maybe you choose one value and then you will delete a value from another variable. So if you delete a value from another variable, you may cause another impact. So that means you will check other types as well. So that means we propagate that update to the next constraints, other unchecked constraints. So that means here we check all of them. There's no new changes. Okay. So forward checking propagates information from assigned to assigned variables, but doesn't provide any detection for all failures. Okay. So let's look at for this example. So this is same as previous cut. So same as here till here. But here, in fact, you can find when we delete, we assign a Q to be green, and then we delete green for NTSA and NSW. We reach this one, NT, NSW, and SA cut. We reach this one. So that is exactly this cut. But you can find, just because we stop checking other conflicts, we don't detect this failure. In this step, we perform further checking. So that means, for example, this one there's a tie as well. So NA cannot be equal to SA. But for here, is there only one value there? You didn't check, right? If you check, you already find the failure. You don't need to perform the next one to find the next variable to assign the value. Okay? So this is NA and SA cannot be blue. Both cannot both be blue. Okay? So that means only one. Okay? Only one. They cannot be equal to each other. So that means we need to perform the constraint propagation. So that means in our implementation, we need to perform just like what, for example, you have choose something, and then you need to add all the constraints to the queue, and then you are not missing this constraints checking. Okay, this is the basic idea. So we call the constraints propagation. We repeatedly enforces constraints locally. So that means even we delete, okay, we got a new states, and then we also perform the constraints checking for here. Okay. So this is the next one. We call the, if we perform both the forward checking and the constraint propagation, and then we said this is arc consistency. This is the simplest form of propagation, makes each pair of variables consistent. What is the arc consistency? Okay. For example, we write like this way. For example, x implies y is consistent. So we define this definition if and only if for every value of x there is some allowed value of y. We said there is an arc consistency from x to y. Okay, this direction is also important. So that means x implies y, means x can choose any value, it will get y. Okay? So that means this implies is really like so for example, everybody is great, and then Tom is great. Okay, we implied because Tom is a people, and everybody means every person. So because Tom is a person, and then it implies Tom is great. Okay? So this is the same idea. That means everybody, Tom, and then John, and then everybody. Okay? everybody, Michael and so on. So that means we implies. So for all the possible values from X, you have a choice for Y. Okay, so that means you can choose whatever value. So there's no restrictions on Y. So that means they're consistent. Okay, there's consistent. X can choose any value. But if you cannot, for example, you can only choose some of them, then there's no arc consistency. Okay? So that means only some people are great. Okay, we need to decide which ones are great. Okay, so this is the reason. Let's look at the arc consistency here. For example, if we reach this state, so we have NT is one value, Q is this value, NSW is only 2, and the V this one, SA this one. And then we want to check whether SA and NSW has the arc consistency. Arc consistency, that means if we choose any value, you can choose a value for the Y. Okay? This X, this Y. If we choose the blue, whether we can choose the blue again for NSW? Yes, there's no problem, because NT and is SA, correct? Is SA, not NT, NSW. SA choose blue, and then NSW is labeling, correct, to it. So NSW cannot choose blue. If this choose blue, this one cannot choose blue. But whether there is some allowed value for NSW to choose? Yes, because NSW still has a value to choose. So if for every value of X there is some allowed value for Y, that means Y still can be assigned. Okay, it can be assigned. So this is the arc consistency. Okay, this is consistent. Let's look at we said direction doesn't matter. Let's look at the NSW to implies SA, whether this is there's arc consistency. Okay, whether NSW implies SA. And then if NSW choose any value, whether we have a value for SA. For red, there's no problem. NSW choose red because we know NSW and SA they are labeling. So NSW cannot be equal to SA. And then if we choose red, we can choose blue. But if we choose blue, you will choose empty, correct? So NSW cannot choose anyone, no value. So this is not consistent, correct? Not consistent. Okay. Okay, this is the idea. Okay, let's look at. So when checking X implies Y, we throw out any values of X for which there isn't a node value of Y. So if you check this one, we throw out any value of X which there's no allowed value for Y. For example, like this one. Because this violates the arc consistency, so we cannot choose that value. Because if you choose that value, there's no allowed value for its tied variable. So that means this is based on the arc consistency. We can delete some values. We can reduce the legal value set for some variables. Okay. And then if X, for example, X loses a value, all pairs Z to X need to be rechecked. So that means this is, for example, when we perform this arc consistency, we found this is not arc consistency. If we choose this one, so that means the arc consistency was violated, and then we also at the same time we delete this one. And then just because we deleted this one, we need to check what? Check all the variables to these variables. Why we don't check this variable to other variables? Later we talk about. First one, we need to check this one to this one. So now the legal values has been reduced. So this one will perform some constraint to other cat like NT to SW, no problem, but like SA is cat like SA to NSW. For this arc consistency, SA to NSW, because you have deleted this value, and then now this one need to be checked again, cat. So that means whether you will delete a value which violate this arc consistency. So all pairs Z to X need to be rechecked. Okay, so let's look at for V to S to this one. There's no problem, but for here you can find V to NSW has deleted one more value just because of this one violate the arc consistency cut. So you cannot choose red for V because there's only one value for NSW to choose. V and NSW, there's relationship cut. They are labeling, so the arc consistency. So we said arc consistency must have a relationship. You cannot check you can check W on this one, but they are allowed. Okay? There's no data constraints, so you just need to check within the constraints scope. Okay. So V to NSW has this issue. Okay? So that means this one also need to checked, because this one has been checked, and then also need to check all of others to this V. Okay? So you can find V is labeling with 2 SA and NSW. So you need to check it again to this one again, and then SA to this one again. Okay, and then so you can find SA can choose one value, and then there's no problem, you can choose green, so this one no problem. And then SW to V, choose this one, you choose either these two. So there's no more violations to the arc consistency, right? So we can stop. So this one update is already done because you check all of them. So let's look at the previous question. We said why we don't need to check if X change. We don't need to check Z. This is just based on the definition, right? We said that for every value of X, there is some allowed value for Y, or we can say there's some allowed value for Z. You delete one, does not matter, right? Like for example, use red, you can find one value, one color, so make Y hold. So you just it's or, right? It's and, yes, exist. If you delete this one, others still hold, right? Because there's no impact for other values checking. For each value, whether there's a allowed value for Y, and then you just checking one less value. So of course, others still remained hold. Okay? So this is the reason we don't check from X to others. We check only others to X, because you will have reduced the legal values for this X, for the implied one. Okay? For the implied one. So whether the previous one hold, we don't know. Okay, we don't know, because you have less choices in the X. So if we choose some value, and then that value has been deleted from the X, and then there's no possible values to be assigned for the X now. So this Z to X does not hold now. So this is valid. Okay? So that's why we need to check Z implies X. Okay. Let's look at so SA. Okay, SA to NT. So for the previous example, okay, for the previous example, if we apply the arc consistency, then we can detect the failure earlier, because we know SA and NT they are tie between each other, and then we perform the arc consistency checking, and the SA and the NT is not consistent, is not arc consistent, because if you choose a value, every value from SA, there's only one value. If you choose this one, there's no value to choose for NT, right? So this is a failure. So arc consistency, we detect failure earlier than forward checking. Okay, so that means we perform, this is like the backtracking. You can use forward checking. Forward checking is 1, and then but improved version is called arc consistency. Okay, for arc consistency, this one is better. So now we have an arc consistency algorithm. Let's look at how it can be run before or after each assignment. Whether you perform the arc consistency detection first or you perform assignment first, doesn't matter, correct? Because anyway you have to do assignment and then to check. Okay. So this is the arc consistency algorithm. Let's look at this one. For the arc consistency algorithm, it's the idea. Of course, this one only focus on the arc consistency itself, and then for the backtracking part, we still use the previous one. Okay, so we just improve, that means add this step when we do the assignment. For example, you first do the assignment and then do arc consistency, or before you do the assignment, you perform the arc consistency. Let's look at this algorithm. So arc consistency version 3. Okay, anyway, we may have multiple versions. This is version 3. So CSP is the problem definition, have all the constraints, definition, variables, domains there, and then it will return the CSP, possibly with reduced domains. So that means for this arc consistency, the return is still the CSP problem definition. It's just update the current state. We just only to update. If we found some violation, we delete the values from the variables, like previous. We said we delete. So your target is just like you want to reduce the search space, so you want to delete some values from the variables as many as possible. Delete as many as possible values from the legal values for each variable. Okay, and then input is CSP, which is a binary CSP with variables x1, x2, xn. Why we call it binary CSP means whether we binary CSP. So maybe this is just like we want to assign a value is 0 and 1. So it doesn't matter. So you just think about it as a CSP problem, and then it contains n variables. So sometimes we call it binary is like the logic, okay, whether it's true or false. We choose this one or not choose this one. So this is just when we talk about that problem, we said this one, but this one is general. Okay, algorithm idea is general, x1, x2. So that means binary means this value can be only 0 and 1. That means for these domains, only two values to choose. So that means for example, like assignment, whether I assign the assignment to you or not, whether we have this class in this classroom or not, this is a binary, only 2 choices. And then local variables, we have a queue. So this is the structure queue. What's the queue? The contents is a queue of arcs. Okay, arcs, because we have that arc consistent detection. So this is the queue of arcs. Initially is all the arcs in the CSP. So that means all the possible arcs in the problem just inserted into the queue. Okay, into the queue. And then why we contain this queue, just because later we want to insert and delete. So this is the reason. Let's look at why the next is a loop. Why the queue is not empty. So this one will check all the arc consistency. So during one checking, we may need to do propagation, right? We may have more constraint. We add more arc into the queue, and then once we finish one, we delete one, right? So we will first remove one, and then check if we find it causes more arcs. We do insert into a queue. We keep doing till the queue is empty. We perform the arc consistency checking for the current state, and then now we can move on to the assignment. So this is the ideal. Okay, so for this algorithm, they have two. Okay, this one call another function. Okay, another function. Let's look at, as long as the queue is not empty, we first find the first queue, okay, first item from the queue. Remove the first. Remove, that means this one will not be existing in the queue anymore. So for example, this queue first item is xi, xj. If we remove inconsistent values xi and xj, so this is a function. Okay, it's a function. So that means we perform the arc consistency checking here. Okay, so this is the arc consistency checking only. Okay, the implementation is here. Why we perform this one? Because this is relative independent. Is repeatedly called, so we can do a maintenance easily. We see the clean rather than put this logic into this one, make it more difficult. Okay, it's a modular design. Okay, and then for each xk, for example, if we already finished the arc consistency checking, and then for each xk we will do this one. What is here? Each xk enables xi, and then we'll do add xk to xi to the queue. So this is the propagation. Okay, we mentioned this one before. Okay, you have to do further checking. Okay, if there's a looser value, so that means during the arc consistency checking, looser value, that's why that function will return true. Okay, if it's no, then you don't need to do that one. Okay? And then you will check all the arc consistency which has the x, has that variable as the implied variable. Okay, so this is the reason. So this is perform the propagation. Okay, propagation. So if this is true means here you can find if removed is true, and then we can have this. We have this one. So add xk to xi to the queue. Which xk will be added to the xk xi to the queue? It's only the labels. Labels. If this xi has a label xk, and then you will input. Okay, sorry about this. Okay, let's continue for the next. So that means for each labeling xk, we insert xk implies si for this direction, okay, into the queue. And then this is the idea. We first check the arc consistency, and then if there's any value removers, we need to do a propagation. And then let's look at this arc consistency. So the basic idea is that we need to check whether for every value for this xi there's a value for xj. Right? So remove inconsistent values. So that means if there's some value in xi which violate the arc consistency, we need to remove it. Okay, we first just note it down. This is a value to be removed. Okay, and then return the true if it succeeds. Firstly, we set removed indicate this one is false. We don't remove any value from xi. And then for each x in the domain xi, that means for each value in the domain xi, we confirm. If no value y in domain xj allows xy to satisfy the constraint xi implied xj. So this is implied. I think there's a typo here. Should be this way. Satisfy the constraint xi implies xj. So that means if for one value there is no value for y to satisfy the xi implies xj, then we said this value is illegal, correct? So we need to delete x from the domain xi. So that means the domain has been, now you can just use domain, means legal values set. Domain has been reduced to a smaller space, and then can speed up our search. And then also indicate the removed will be true, and then return the removed. Okay. So that means this is only just like the checking cut. So that means this is like you can find out we exhaust all the values in the xi, and then if it violates this one, we remove that value. And if there's any one remover, we indicate a true cut, we are true. And then that means xi's domain has been changed, and then we find all the xk to xi's arc, insert into the queue to do further checking. So go with this one. So the queue will be increased, cut, we increased, or just will be updated, and then keep doing. So this arc consistency will help to detect the failure earlier than the forward checking. Right? This is the basic idea. That means basically you just use the backtracking plus arc consistency is already good enough to detect the failures earlier. Okay. So that's all for this chapter, and the remaining several slides is only very short description. So for example, besides arc consistency, whether we have some other things to improve. In fact, we have a path consistency and a k consistency. So for this one, if you're interested, you can have a look, but it's not required for us for here. Okay. And then the complexity for this algorithm is big O m to the power of n. So that's worst case. We have this one. This is depending on the number of leaves on the last layer. Okay. So this one is worst case is equivalent to the brute force search. But can we do better? So we have that we can perform local search. We didn't cover that one, and also perform prefers. We mentioned the different consistency, k consistency, path consistency checking, okay, and forward checking and arc consistency. Okay. So that's why we already mentioned the kind of backtracking search. Initially one is this one, but we perform the arc consistency can detect the failures very early, and then it will improve. And then we can further use path consistency, k consistency, and the local search to further improve it. Okay. And then the last slide, we just do a review for the CSP problem. So CSP is a special kind of search problem. It stays defined by value and for a fixed set of variables. So that means you have a list of variables to assign values. These variables can be represented for anything, for courses, classrooms, and tasks, okay, and so on. And the goal test defined by constraints on variable values. So that means we perform the goal test based on the constraints on the variable values to see whether all the variables had meet the constraints when we assign a value to it. And then we perform the backtracking search. Basically it's a DFS, but we do layer by layer. Each layer we only assign one variable assignment, perform one variable assignment, where success states are generated by considering assignment to a single variable. So variable ordering and value selection. That means okay, let's continue for the next one. So the basically is we use DFS as a foundation, and then we improve it by each time we just only assign finish assignment for one variable. Okay, so for each layer, and then we want to improve this one by some other mechanisms. So we use variable ordering and value selection. These two strategies. That means which variable to search, to assign first doesn't matter, and even we find the variable which value to assign first, to try first, also matters. So that means we use these two heuristics. And how to develop a strategy for these two heuristics? We have a forward checking. So this one we prevent assignments that guarantees later failure. That means we can detect failure earlier rather than just when we reach there we find that it's a failure. So we do forward checking. So basically we use the most constrained variables and the least constraining values to do this. And then the main thing, maybe we can use most constrained variables and then decide which variable to use. Okay. And after that we can perform the least constraining values. And then we also use arc consistency. That means we want to perform the propagation of the constraint checking. When we change something, we also need to detect whether there's a cause any additional values drop for some other variables. So that means we want to remove those values from the variables. So that's additional work to constrain values and detect inconsistencies. Okay. So that means if there's some inconsistency, we can detect failure early, and then if there's more constraint on others, we can remove the values. Okay, remove values. If there's no arc consistency, we can remove the values, and then all the variables which implied this variable need to be checked. All the labeling, okay, all the labeling variables. And then to further improve this one, we can try different algorithm we mentioned. You can use local search, but we didn't cover that one. And the complexity of CSP is NP complete problem. So NP means non-polynomial. That means it cannot be solved in a polynomial time complexity algorithm. Okay, NP complete. In general, that means exponential worst case running time is this one. But in fact, we can improve this one by a lot based on the previous strategies. And then for this CSP, we have some application. For the first one is called SAT, called satisfiability assignment task. Okay, problem. For example, you have Boolean vectors, whether you want to assign true or false to those Boolean variables. And the graph coloring. Okay, you have a graph, and then you want to have different colors for different nodes. Also NP complete and also CSP, okay, CSP problem. And the efficient solution possible for special cases like the tree structured CSP problems. Okay. We didn't cover that part. In fact, we can use topological ordering, and then we can improve it further. But anyway, the most important thing for this one is that how to define a CSP problem, and what is the backtracking algorithm, and how to improve it based on forward checking and the constraint propagation. That's the main things. Okay, you also have several questions in the homework 3 related to these things. And if you have any problem, just feel free to contact me, and I will confirm your group formation today. And then if you didn't join any group, I will just assume you want to do the project independently, so I will add you to an empty group, and then I will try my best to reply to your inquiries related to the programming and so on also by today, and then maybe start grading your homework 1. Sorry about the delay, just because of too busy and yeah, really time consuming in preparing the videos. It's more like the classroom face-to-face teaching, so this one takes more time. Okay, I will try my best to catch up in grading as well. Thank you. And next week we'll continue with the deep learning or machine learning part. That will be a very excited module. If you have time, you can just perform some initial preparations. For example, I will release the maybe PyTorch environment setup tutorial earlier in the next module. So maybe during the weekend I will do that and release the related slides. And then of course we start with basic machine learning algorithms first, and then neural networks, and then deep neural networks, and then convolutional neural networks, and then maybe GAN as well. GAN is based on the adversary search we mentioned before in the game. And then you have two things, generator and the discriminator. They compete each other. Each one will be improved, and then we can generate a realistic images or scenes. Just like we can generate fake data, which is cannot be discriminated by a human. You assume this one is real, like a true data. Okay, see you next week, and then have a nice weekend, and then take care of yourself and stay healthy.